This video demonstrates how to conduct the static structural analysis on a leaf spring. Here, the main intent is to demonstrate the boundary conditions and the loading on the leaf spring. Hence, the whole assembly of the leaf spring is simplified to a single part. It can be observed from the behavior animation of this leaf spring that one end of the leaf spring is constrained in translation in all three directions and allowed to rotate along the axis of the cylindrical surface. Whereas on the other end, the cylindrical surface is allowed to rotate about its own axis and also is allowed to translate in the x direction. How these boundary conditions can be accomplished? Those all things we will discuss in this tutorial. Let us begin with the tutorial. Create a new static structural analysis file. Right-click on the file, pick on Rename. Enter the name of the file as Leaf Spring. We are going to make use of the default structural steel for the analysis. Pick on the geometry, right-click, pick on the import geometry. The leaf spring.stp is already there in the temporary memory. Hence, let us use that CAD geometry. You can observe a tick mark which dictates the geometry is loaded. No need to open the geometry since it is a single part. There is no geometrical defeaturing or surface splits are involved to define the contact. Pick on the model directly. Right-click, pick on Edit. This will take us to the mechanical window. The geometry is imported in the mechanical window. As I discussed earlier, the whole assembly of the leaf spring is considered as a single body for the simplicity, because here the main intent is to demonstrate the boundary conditions and the loading for the leaf spring. Leaf spring has two eye ends. To define the boundary conditions at each of the end, let us define the respective Cartesian coordinate systems. Pick on the coordinate system in the outline tree. Right-click, pick on Insert, pick on Coordinate System. Right-click on the new coordinate system, pick on Rename. Rename it as CSO01. To define this coordinate system, a geometrical reference is required. Pick on the geometry here. Ensure that the surface is selected in the selection filter. Pick on the cylindrical surface. Pick on Apply to confirm the geometry selection. It can be observed from the type of the coordinate system as Cartesian. Right-click on the coordinate system, pick on Duplicate. Rename this coordinate system as CSO02. The geometry of the new coordinate system need to be replaced by the right end cylindrical surface or the other end of the leaf spring. Pick on Apply. Currently, we have three different coordinate systems. The first coordinate system, which is the global coordinate system. Also, two different coordinate systems named 1 and 2. Once the coordinate systems are defined, let us proceed to define the boundary conditions for this model. Right-click on the static structural, pick on Insert, pick on Remote Displacement. Under the geometry, pick on the first cylindrical surface and pick on Apply. Observe that the coordinate system should be selected as 0, 1 and x, y, z ordinates should be made 0 for this remote displacement because we are defining the remote displacement for the highlighted surface with respect to the new coordinate system. Hence, the coordinates should be 0, 0, 0. As we discussed earlier, based on the simulation or based on the animation, that this particular end should be restricted in all the directions for translation. Hence, the translation degrees of freedom should be constantly 0 for x, y, and z. But as far as the rotation is concerned, about the z-axis, the body should be free to rotate, or the highlighted face should be free to rotate, but it should not be allowed to rotate about the x and y axis. Hence, the x and y axis should be constantly 0. Let us review the boundary conditions for this particular end. It can be observed that this particular remote displacement happens to be acting with respect to the new coordinate system. Hence, all the coordinates are 0, 0, 0. Similarly, the translatory degrees of freedom are 0. The rotational degrees of freedom are 0 for x and y only and is free to rotate about the z-axis. Once the boundary condition is defined for the first end, let us proceed for defining the boundary condition for the second end. Right-click on the static structural, pick on Insert, pick on Remote Displacement. Under the geometry selection, make sure that the surface is selected in the selection filter. Select this particular cylindrical surface, pick on Apply. Similar to the earlier case, the location of the remote displacement should be 0 in x, y, and z with respect to the coordinate system 2. The translation degrees of freedom should be defined as follows. This particular end should be set free to translate along the x direction. Hence, x should be free. Y should be constantly 0. Z also should be constantly 0. As far as the rotation is concerned, similar to the previous case, the cylindrical surface should be allowed to rotate about the z-axis with respect to this coordinate system and should not be allowed to rotate about the x and y. Hence, the x should be made constantly 0. Y also should be made constantly 0. Z is free. Review the boundary condition or the remote displacement for this particular end. Once the remote displacement for both the ends are defined, let us apply the displacement constraint for the leaf spring to deform the whole body. Right-click on the static structural, pick on Insert, pick on Displacement. Select the bottom face, pick on Apply. It should be defined by the y displacement of 5 mm with respect to the global coordinate system. Observe the coordinate system is global. X component should be 0. Z component should be again 0. At this point of time, we have defined the boundary condition and the load. It is the time to define the mesh. Right-click on the mesh, pick on Insert, pick on Sizing. All the faces should be sized with the element size of 5 mm. Hence, make sure that the surface is selected in the selection filter. Pick on, right-click, pick on, select all. This is going to select the surfaces of the leaf spring. Pick on, apply. Right-click on the mesh, pick on, generate mesh. This will take a few seconds of time to update. The face sizing need to be maintained fine. Remesh the model. Pick on Generate Mesh. Now the elements are found to be finer compared to the earlier case. Earlier, we did not specify the element size. Hence, the default element size was used for the meshing purpose. Pick on the mesh. Let us look at the statistics of the mesh. This mesh contains approximately 37,000 nodes. Let us proceed for solution of the problem. Pick on Solution. Right-click, pick on Solve. The solution status can be monitored from the progress window. This will take a few seconds or minutes of time to solve. The solution is completed. Right-click on the solution, pick on Insert, pick on Deformation, pick on Total. Right-click, pick on Evaluate all the results. It can be observed that the deformation is exaggerated or the behavior is magnified for the clear visibility. It can be seen from the result scaling as 5.5 times the actual case. It can be changed to 1:1 true scale. Right-click, pick on the view, pick on the front view. You can observe the 1:1 scaled deformed model. Pick on Animate button. The behavior is as expected. For the better clarity, the scale factor can be changed to 2 times. Let us animate this behavior now. We can change the number of frames to 100 and the end time to be 10 seconds for the smooth animation. This is the behavior what we have expected. It can be seen the left end is not translating, but whereas it is rotating with respect to the axial direction. Similarly, at the other end, we have given the boundary condition to translate also and to rotate also. You can observe the translatory as well as the rotary motion. Once the behavior was predicted to be accurate, we can proceed for determining or evaluating the other results like elastic strain and the von Mises stress. Right-click on the solution, pick on Insert, pick on the stress, pick on Equivalent von Mises stress. Since we are using the steel material, we look forward for the equivalent stress in the body. Similarly, right-click, pick on Insert, pick on Strain, pick on the equivalent von Mises strain. Right-click, pick on Evaluate all the results. Results are evaluated. The stresses generated in the body can be seen. Similarly, the strain. The behavior can be seen clearly by plotting the results in the different windows. For example, let us split the windows into two vertical viewports. The windows can be minimized for the better visibility purpose. Let us plot the displacement counter in the first window. Pick on the outline, pick on the total deformation. In the second window, let us plot the stress behavior. Pick on the outline, pick on equivalent stress. This is how we are going to make use of the remote displacement for giving or controlling the surfaces or the geometrical entities in the desired direction. Either it can be translation or the rotation. Thank you for watching this video. For more videos, please visit my channel, or you can contact me on engineeringtutorsdesk@gmail.com. For more videos, you can visit my website https://sites.google.com/site/FEA engineering design/. If you like this video, please press the like button. If you want to be notified for my new uploads or for my new videos, please pick on subscribe button just below this video. Thank you again. See you with the more tutorials.